Yeah, this is the introduction for Workshop 6. So, Workshop 6, we're going to start to explore radicals. Now, in the previous workshops, we did all sorts of different things. We looked at quadratics, we looked at polynomials, we did all sorts of different things. The one thing that I want to emphasize is, again, topics just simply build upon one another. They're just extensions of the previous. And if as you can see throughout this course, if you're focused on that pattern, the pattern just holds true with every workshop and every topic. And just like way back when you guys were learning about addition, you guys ended up learning about subtraction just after as little kids to go backwards. Then came along multiplication, which was repetitive addition. And now to go backwards, we divided. And then, even in this course, we had these binomials and we FOILed them, so we multiplied them. And then we undistributed, or another word for undistributed is factored. And we want to learn how to go backwards there. And so that's actually going to hold true again here. So in this particular workshop, we're going to deal with some radicals. Now, radicals is kind of like having those exponents, but going backwards. So previously, we were working with exponents, rules of exponents, did all sorts of things. And now we're introducing radicals. And radicals are just simply going to just have us applying those exponents by going backwards. And so that's the essence of this topic. And we're just going to explore it. We're going to do all sorts of different things with it. Just like we did with the polynomials and combining like terms, we're going to do the same thing here. We're going to combine things that have similar exponents, similar radicals, addition, subtraction, multiplication, division. We're going to do all the same operations, just simply with the radicals. So just an extension of what we've done previously. And so, yeah, these are going to look kind of new, a little bit of new notation. But don't worry. If we work through the topic step by step, you'll see it's just simply another extension. So let's go through this workshop. Make sure you see all the different assignments that are there for you. Now this workshop is very similar to workshop 3. And so for this workshop, if you take a look, once again, we have preparation here. And then with the preparation, so we have in that link, if you remember, that's the link that has a lot of those video resources and different tutorials as well. But looking at the assignments, let's take a look at the assignments. And for the assignments, we have the devotional. We have one math discussion, but again, because it's similar to workshop 3, there is not a second discussion, or a second math discussion. There's not a self-reflection. It jumps right to the homework and then your final exam. And so we took out that extra discussion because we knew that we wanted to make sure you had time to concentrate on that final exam. Then, of course, you have the end of course survey. So just make sure that you email me the confirmation, and that is worth an extra 10 bonus points. Make sure you send it to me. In case of a class audit or something, they want me to have the quote-unquote confirmation that it was completed. So just make sure to send me a quick note that you completed it, and we're good to go. All right, so once again, just make sure you let me know if you need any assistance. And right after this little intro, I'm going to have a radical review. It's again, just like this last workshop, about a 30-minute review video that goes through a bunch of different topics for radicals. And now keep in mind, there are some other videos that I did make, but they were from previous courses, and they go into some of the more advanced equations. That is listed right here in the workshop 6 announcement. So you can watch those as well. That might help you with some of the equations. But this review video that I made covers the majority of the topics that are for the workshop. So make sure you just let me know if you need assistance. I'm here for you. And let's rock and roll. Last workshop.
Alright, this video is just to go over some examples for radicals and also rational expressions. And so what you're going to find when I go through these different examples, there's all sorts of ways to interpret these questions and many ways to simplify them. And just like for this very first one here. For this very first one, we have the 3x, we have 54x. Well, when you have radicals here, one property tells you that if you have multiplication, now key here is multiplication, or it could be division. If that was addition, you would not be able to do this. So we have 3 and 54, so 3 times 54 and then x times x. So we can go ahead and do 3 times 54. And that gives us 162. Alright, so we have root 162. And then we have x times x, which is x squared. So that's not quite simplified yet. We have to make sure we take out any perfect squares that might be in there. Well, what's a perfect square? Well, 1 squared is 1, 2 squared is 2, or, oh wow, 2 squared is 4. And let's actually put this down. So 1 squared, 2 squared, 3 squared, 4 squared, and so on. So the result of those are perfect squares. So 1, 4, 9, 16, and so on. So let's take that 162 and let's just try to see, hey, what kind of perfect squares might go in there? Well, let's start out with some 4. Let's start with 4. 4 does not go in there. So let's try a couple others real quick here. 36 does not go in. So those weren't working. Let's think a little bit more strategically. Instead of just randomly trying numbers, let's think about the breakdown of this 162. Well, first off, 162, it is divisible by 2, so let's try 2. Divide by 2. We get 81. Oh. Well, there's our perfect square. So 81 is our perfect square. That's 9 times 9. But what I was going to do is I was going to break the number completely down. But hey, we ran into our factor here, our perfect square. So 81 is a perfect square. That means 162 is the same thing as 2 times 81. And then we also have that x squared in there. Now, since this is a square root, anything that's a perfect square, we can take the square root of. We can take the square root of 81, which is 9. Now, x squared, that is also a perfect square. Now, if you think about it, the square root of x squared is going to be just a single x, because we have x times x is x squared. So that's going to come out as an x. And once it comes out of the square root, it's no longer there. So we took care of the 81, took care of the x squared, and what's left in there is just a 2. Can you really take the square root of 2? If you try to take the square root of 2, you end up with an irrational number. So let's take a look at number 2 here. We have square root of x to the third. Well, what we want to do is we want to focus on the perfect square. There is a perfect square in there. That x cubed can actually break up into x squared times x. And so there is a perfect square. It's x squared. It's just times a single x. This kind of plays on the whole properties of exponents. Because if you have the same base, you can combine the exponents. 2 and 1 give you 3. So we can take the square root of x squared. So we're left with x square root of x. Alright. Now the next one over here looks rather unique and pretty complicated. But it's not. So let's just go step by step here. Remember from the first example, I said that, if you have multiplication and division, we can actually combine those radicals, combine those square roots. And so, for this one, we can combine those. We can put them underneath 1 square root. And so, after we put on the 1 square root, we can actually simplify this to make it a little easier on ourselves. Alright, so 350 divided by 7. Ooh, what in the world is that? 350 divided by 7. Ooh, 50. Here we go. So that's going to end up being root 50 Now we have this here is a rule of exponents. 8 minus 1 is 7, so we have x to the 7th. That's not quite done yet. That's not done yet. There's a perfect square in the 50 and in the x to the 7th. So the perfect square in the 50 is actually the easier one. 50 is the same thing as 25 times 2. So 50 is the same as 25 times 2. Now x to the 7th, well, the variables are actually really easy. Since we're doing the square root of 7, we can actually take that 7 and divide it by 2. What in the world do I mean by that? Well, square roots, if we think about this is actually jumping ahead to the next workshop, or it might actually be later in this workshop. A square root is the same thing as a half exponent. So this can actually be rewritten like this. So 50 x to the 7th, but then the parentheses around that whole thing, and it's going to be to the 1/2 power. I know it seems kind of weird, but square roots are the same thing as 1/2 power. And so that's why we can take that half power and put it to the 50, which means square root. 1/2 power is square root. And now we have the rule of exponents. 7 times 1/2 is 7/2. And so what that's going to tell us is we can actually do 7 divided by 2, which is 3. So 7 over 2 is 3, but we end up with 1 left over. We end up with a 1/2. So when you have these variables, there's actually a really easy pattern. Here's the easy pattern. If it's an odd exponent, you're always going to have 1 left over. Because anytime you divide it by 2, you're always going to have a remainder of 1. Anytime it's an even exponent, well, that even exponent is going to be able to be taken out of the square root. And so this is not part of this question. So if I say, hey, square root of x to the 10, well, that can be broken up into x to the 5th times x to the 5th. That's a perfect square. 10 divided by 2 is 5. And so that's the same as x to the 5th. Now, what if that was x to the 11th, though? So what if, now a completely different question, what if that was x to the 11th? Well, 11 divided by 2 is 5, but there's a remainder of 1, and that remainder is going to remain in the square root. So that's going to end up being x to the 5th square root of x. And so when you divide by 2, that's basically using that rules of exponents to show you, hey, I want to have a variable left over on that inside. So let's clean this up. So this x to the 7th there, so that x to the 7th is the same thing as x to the 6th times x. So if you notice there, we have 2 parts there that are not perfect squares. Those 2 parts are this 2 and the x. So those 2 parts are going to still remain in the square root side. Now we can take the square root of 25, which is 5. We can take the square root of x to the 6, which is x to the 3rd. And we are left with, inside that square root, basically it's kind of like our remainder, 2x. Okay, a lot going on there. If you need to, just go ahead and pause the video and just rewind it and just take a look at the explanation again. Alright, next part, number 4. So number 4, now this is where square root starts to get a little unique. So now we have addition and subtraction. So number 4, 5, 6, addition and subtraction. This is actually so much easier than what it looks. For here, for example, everyone knows now that you can do 4x plus 5x, and we know that that's going to equal 9x. Whenever you have addition and subtraction, you can combine the terms if the square roots are exactly the same. Just like combining like terms with variables. If the variables are exactly the same, including exponents, exactly the same. We can combine them like terms. So the final answer for this is not 9x, but for this one, it's going to be 9 root 7. Now number 5, that's 4 root 13x minus 8 root 13x. The square roots are the same. Therefore, I can just simply go 4 minus 8. And 4 minus 8 is negative 4. And our square root is at 13x. So those square roots end up acting like variables here. It's kind of odd, but they do, because 4, it's kind of like saying 4x minus 8x. Very similar. Now this next one here, they don't match. But we're going to combine what we did with the first couple problems in numbers 4 and 5 to make that 98 look like the second one. So we got to come up with some perfect squares that are in 98. Well, the perfect square that's in 98 is 49. So that breaks up into 49 times 2. We can take the square root of 49. It's 7. So that's going to be 7 root 2 plus 6 root 2. And the final answer, well, not final simplification step would be 13 root 2. Alright. This next example is going to be very similar again. Now we have a bunch of things going on here, but we need to make sure we try to figure out how to get those to match somehow. Now sometimes not all of them are going to match. We might have pairs. So let's take a look at what happens with this problem. So for this problem, we have the 48. Biggest factor that goes into 48. That's a perfect square. Well, let's think about it. 4 goes into it, and 16 might go into it. Well, let's take a look. 48 divided by 16. Bingo, there it is. So 48 breaks up into 16 times 3. 12, well, that breaks up into 4 times 3. 108. Ooh, that's a tough one. 108. What's the biggest perfect square that goes into 108? Well, let's try 16 again. Nope, not quite 16. But let's think a little more strategically here. 108. Well, let's think about a bigger perfect square. That last number is 8. So let's try 4 real quick here. 108 divided by 4. Oh, it does go in even, but so 4 is a perfect square. It's 4 times 27. But the thing is, inside the 27 is also a perfect square. 27 is the same thing as 9 times 3. Now here's a big something that a lot of students don't see this pattern here. There's definitely a pattern with these perfect squares. No matter what you do, if you take a perfect square and you times it by another perfect square, you will always get a new perfect square. So for over here we have 4 and 9. Those are both perfect squares. If I multiply those together, I will get another perfect square. And there it is, 36. So 108 is divisible by 36. Bingo, there it is. So that's 36 times 3. And the 50 is 25 times 2. Okay. Now, if you don't get the biggest perfect square, that's okay. It's just going to be a couple extra steps, and that's no problem. But if you get the largest perfect square, it breaks it down the fastest. So that 108, I could have did the 4, but then I would have been left with 27. Then I would have an additional step to get rid of the 9. But if you get the biggest perfect square first, you simplify it the quickest. So let's go ahead here. Now there's a couple key things for this one. This here is 3 times that radical. And we can take the square root of 16, which is 4. So I'm going to end up with 3 times 4, which is 12 out here. A lot of students will forget about that 3. And also they might forget about the 3 that's on the inside too. And so the reason where we got 12 from is that 3 on the outside times the square root of 16, which is 4. All right, let's keep going. So minus, oh, I almost put the 4 on the outside. Square root of 4 is 2. So that's 2 root 3. And next part, same thing here. That's 3 times. And square root of 36 is 6. So 3 times 6 is 18. That's 18 root 3. And last but not least, we have root 25 times 2. So that's going to be plus 5 root 2. Well, the first 3 match, but the last one doesn't. So that's going to kind of be like, it's not the same as, but it's going to be like x and y. So we have 12 minus 2, which is 10. 10 and 18 gives you 28. So we're at 28 root 3 plus 5 root 2. Alright, let's keep moving here. Number 18 and 19 focus on something called rationalizing the denominator. You don't want to square root in the denominator. And so what we're going to do here is we're going to take the top and bottom and times by, well, what we have here. We're going to times by root 15. And so times top and bottom by root 15. And now what that does, and that's kind of like saying, hey, oh, on the bottom I have root 15 squared. And square root and square, they're inverse operations, so they cancel each other out. So in the bottom, we're left with 15. And in the top, we're left with root 15. Now don't be tempted to try to cancel out those 15s. Don't do that. Because one is in the square root sign, and the other is not, which means you cannot cancel those. But that's a rationalized denominator. For some reason, a long time ago, some mathematician said, hey, to be simplified, we don't want square roots in the denominator. And so that's all that means. We're just taking the square root, just rationalize the denominator, make sure no square root is there. And the same thing's going to happen with this one. Times top and bottom by 7. So on the top here, we're going to have root 14 over 7. And again, don't make the mistake of trying to reduce this to 2. Well, the 14 is in the square root, the 7 is not. Okay. Now for this one, what we have here is we have root 6 plus root 3. We're going to have to actually multiply it by something called a conjugate. And if you remember the last couple of chapters, we had some special cases in terms of, and also in this current week coming up here, it's called factoring. It's called a difference of perfect squares. And so that's what we're going to mimic here. We're going to take the top and bottom and times by what almost looks like the same thing. It's not the same thing, but almost looks like the same thing. Basically, it's the same, except we're going to change that middle sign. So we're going to change that middle sign. And we're going to see what happens here. And so I'll actually put a parenthesis here, and we're going to actually do something called FOIL. So first, outer, inner, last. Root 6 times 6 is 36, root 36. And so square root of 6 times square root of 6 is just 6. And just to show it in the step, 6 times 6 is 36. And that gives us root 6. Root 6 times minus root 3. 6 times 3 is 18. And now we'll go to root 3. Root 3 times root 6 is plus root 18. Last but not least, root 3 times root 3. That's going to be the same as root 9, which is 3. Now, those two middle terms there cancel out. Negative 18, negative root 18, positive root 18. So we're left with 6 minus 3. There's the minus number is right there. So it's minus 3. 6 minus 3 which is 3. So that's what the denominator ends up becoming, just 3. So let's not forget about the top though. Let's look at the top. The top actually had 3 from over here. And then it had times root 6 minus root 3. And then that was all over 3. Now some students, because of what I said before, they would think, hey, I can't cancel those 3's anymore, can I? Well, you have to look at the context of what's going on here. This is 3 times that parenthesis. There's not addition or subtraction there. So I can cancel out those 3's. So those 3's can be canceled out. And your final answer is going to be right here. Okay. Now, let's take a look at the next question here. Next question, I see a little 3 on the outside. This little 3 here basically means cube root. And there's all sorts of calculators out there that help you calculate cube roots. Now, cube root, and now for some calculators, now remember, a root is the same thing as a fractional exponent. So root 3, or a cube root, is the same as 1/3 for an exponent. So some calculators are going to want you to put in a 1/3 for an exponent. Now some other ones, like this simple one here on Windows, actually has a cube root button. So I'm going to go use that real quick. Cube root. Oops, I had to actually technically do cube root twice there. Let's make sure I do it once. Okay, here we go. Cube root of 512 is 8. That's just simply 8. Alright, now, next we have a couple more going on here. Cube root of 1 over 125. Well, let's do those individually here. Cube root of 1 is 1. 125 cube root is 5. So, the 1 is a perfect cube. 1 times 1 times 1 is 1. 125 is 5 times 5 times 5. So the cube root of 1 is 1. Cube root of 125 is 5. So that's the same as 1/5. The next one though, the next one is a little different. Because this one, I have a cube root, and I have this exponent here. It's going to be almost identical to what we did before. But rather than dividing that exponent by 2, we're going to divide it by 3. So 19 over 3. So 19 divided by 3 is the same as 6 and 1/3. Or essentially, it's 6 and 1 remainder. So this y to the 19th, that does have a big perfect cube in it. The perfect cube is y to the 18th power. And in this instance, we only have 1 left over. Is it possible to have more than 1 left over? Yes, it is. Since that's cube root, you can have a remainder of 1 or a remainder of 2. Say you have a 5th root. You can have a remainder of 1, 2, 3, or 4. In this case, we have a cube root, and we just have 1 remainder. So the cube root of y to the 18, well, since it's cube root, we're going to take that exponent and divide by 3. Because remember, it's the same thing as 1/3 for an exponent. 18 divided by 3 is 6. So, that's going to be y to the 6th. And we are still going to have that 1 left over on the inside. And I do have to make sure I make this a little more clear. That is a cube root. Ooh, that 6 almost made it look like it was a 6th root. Oh, it's a cube root. So I made sure I put a different color there. Alright, let's keep moving on here. So this one here is multiplication. I have cube root and cube root. Since they're both the same roots, I can multiply those numbers. So 9 times 15. If they were different root types, you can't do it. So we're left with 135. So we have a cube root of 135. Oh, but that's a big number. I'm trying to find a big perfect cube in there. Well, let's look at the breakdown of these numbers. Let's look at the 9 and the 15. 9 breaks up into 3 times 3. 15 breaks up into 3 times 5. And I just multiplied those two numbers together, which means 135 breaks up into 3 times 3 times 3 times 5. And if you notice here, I have 3 3's. 3 times 3 times 3 is 27. And 27 is a perfect square, and I bet you it goes in evenly. There you go. It's 27 times 5. So this can break up into 27 times 5. And we already know the cube root of 27, it's right there. We just did it. Cube root of 27 is 3. And so we're going to be left with 3. So we're going to be left with 3, and then cube root of 5. Alright. Alright, here we go. Let's keep going. Next one over here. Now we have addition in the middle there. Alright, so now we have that addition, but and remember, just like before, in order to do anything, they have to be exactly the same. So, but when you take a look at this problem, don't be too, don't read into this one too much, because a lot of times students will try to figure out how to get those roots to match. But the thing is, one is a square root, one is a cube root. Can't really get those together. A lot of times what students will do with this question, now this is a mistake, don't do this. What they'll do is they'll say, oh, okay, that's root 2. That 8, oh, 4, 2, okay. So that's root 2 plus 2 root 2. And then they'll say 3 root 2. But what they did was they forgot to recognize that the second one was a cube root. So this is actually technically incorrect. So what's correct then? So let's take a look. So root 2, okay, that's root 2. But that's the cube root of 8. Huh, cube root of 8. Let's take a look here. Cube root of 8. 8 cube root. Oh, that's a whole number. It's 2. Ah, 2 times 2 times 2 is 8. So cube root of 8 is actually 2. Thing is, can't do anything else with that. One's a root sign and one's just a number. Can't do anything to it. That one's actually all done. Alright. Now let's just keep modeling here. And so over here, what we have here? We have 64 to 1/2 power. Well, now we know that 1/2 is the same thing as square root. So that's the same thing as taking the square root of 64, which is just simply 8. Next one, we have 1/3 for next one. Well, now we know that that's the same thing as root 3 of 343. Oh, what in the world is that? Well, let's take a look here. So 343 cube root 7. And that's true. 7 times 7 times 7 is 343. Alright. So what are we going to do with this thing? This thing looks like an ugly mess, this next one here. Well, we have to use the rules of exponents. There's no addition here, so this is just straight multiplication. 8 times 2 is 16, so we're good there. But the next one though, same base. The x is here, same base. What that means is we have to add the exponents. We have to add those exponents. So 1/3 and 1/6. Oh geez, 1/3, 1/6. 1/3 plus 1/6. Well, common denominator would be 6. So that's 6. So that's 2. That's 2 over 6 plus 1 over 6, which is 3 over 6. Okay, so that's 3 over 6, which is 1/2. So 2 over 6 plus 1 over 6 is the same thing as 3 over 6. Let's bring it down just to make sure everyone knows where that came from. And 3 over 6 is just 1/2. So that would be x to the 1/2. Now if you're in my math lab, not sure if they were going to ask for that or for the fractional exponent. Not completely sure. Now, definitely both of those answers are correct. Alright, look at that ugly mess of the next one. Let's see what's going on over here. Alright, so on top we have this 3 exponent on the outside here. That's gonna go into both. And the reason why it's gonna go into both is there's no addition or subtraction there. That makes it a little different if there's addition or subtraction. So we can do 5 to the 3rd power, and we know from above that that's 125. Rules of exponents. 1 over 5 times 3 is actually going to be just simply 3 over 5. And that's going to be over y to the 4 over 15. Now, what we can do here is we can simplify this. The y's there, yeah, the fractional exponents, they look weird. Oh no, don't worry. We have division, and we're just simply subtraction. So that's going to be 3 over 5 minus 4 over 15. Common denominator would be 15. And so, to make that a 15, times top and bottom by 5, sorry about that, by 3. And so that top here would end up being 9. Alright, and so 9 over 15 minus 4 over 15 ends up to be 5 over 15, which is 1/3. And so what we're left with there is the 125, and we're left with y to the 1/3. And now, my math lab might not accept that. It might want you to actually do the cube root sign. Not completely sure, but it might want you to do the cube root sign. Oh, that was a 5. Something like that. Alright, so this was a review of radicals and also the expressions with rational exponents like fractions and stuff. If you need any more help or more assistance, please make sure you email me, text me, or post in the faculty forum. Hope you guys have a good weekend.